Okay, welcome to lecture 15 in metallurgy. In the last lecture, we have started heat treatment and studied annealing and normalizing. And today we are going to start with hardening, and then the rest of the heat treatment processes will be discussed in this lecture. So first of all, hardening. Hardening is a very simple process of obtaining very hard structure in terms of hardness. That means the product that is formed for steel because of hardening is it's basically called martensitic structure, and that product shows excellent hardening property. That means hardness properties. For example, the hardness is maximum 64. Rockwell hardness can be Rockwell hardness can be obtained when we do hardening in the steel. And also this hardness of the steel depends on the carbon content. If the carbon content is higher, then the hardness is also higher. And how do we do hardening? To conduct the hardening, first we need to heat up the material, heat up the steel above the upper critical temperature range, and then we cool it suddenly into the brine. Brine or maybe in the water can also work sometimes, but brine is much better because it provides better cooling rate. That means higher cooling rate can be obtained by using brine. Brine is a solution of sodium silicate in water, which actually reduces the water temperature. And because of that greater difference in temperature, hardening is much better compared to the normal water cooling. That means for hardening, you have to heat up the steel above the upper critical temperature to form 100% austenite, and then you cool it very fast. Then you will obtain a hardened structure. And usually in the case of slow cooling, carbon atoms that are trapped inside the matrix of iron diffuses out of the austenite to form BCC structure. But when you do the slow cooling, that occurs. But when you cool it at a very high cooling rate, then this transformation from gamma iron, that means austenite, to alpha iron, that means BCC structure, cannot be obtained. In that case, actually, there is not enough time to diffuse the carbon atoms out of the iron structure, and because of that, the carbon atoms are trapped inside the FCC structure of the austenite, and then because of that entrapment of the carbon atom, the crystal structure also changes. That means it does not transform into BCC structure, but instead the structure is a different one. It's kind of a elongated structure that can be obtained, and that resultant structure, which is elongated because of the trapped carbon, which could not come out of the FCC structure to form BCC structure, and that structure is called the martensite. And the whole purpose of hardening is to obtain martensitic structure. If you look at the martensitic structure, it is basically a supersaturated solid solution of carbon trapped in a body-centered tetragonal structure. That means it has a tendency to transform into body-centered cubic structure, but because of the trapped carbon that could not come out from the BCC structure, it actually forms a tetragonal structure, which have side A and side B similar, but side C is longer than A and B. And that is why the microstructure also shows a slightly different structure. We'll see that. And because of the carbon atom that could not come out of the iron matrix, this solution is called the supersaturated solid solution. And the highly distorted lattice structure, that means that's what I said, like tetragonal structure which have A and B side are same, but C is greater than both A and B. So it is a distorted structure, and that distorted lattice structure is the main reason for high hardness of the martensite. Because of that, actually, there is a huge amount of localized stress is developed, and because of that stress, it shows a very high hardness. Okay. And that because of that localized stress, the other matrix, that means the ferrite that is present in there, that means the iron matrix is actually plastically deformed and become very hard, and that is why the hardness is also higher. And the microstructure, if you look at the microstructure, it is kind of a needle-like structure is obtained. It's like this because of the distorted lattice structure. The grains that are formed is under the microscope. If you look under the microscope, then you'll see this kind of a structure where it looks like there are many needles have been placed in the matrix of ferrite, okay, or in the matrix of iron. That's how the martensitic structure looks like under the microscope. Okay, any question?
স্যার মার্টেনসাইটের কি বলে এটাকে হার্ডনেস মেশিনেবিলিটিটা কি স্যার মানে ব্যাড অর
Definitely bad because of that elongated and highly residual stress in the matrix. Martensite is very hard and it is very difficult to cut. Okay, and it's a very brittle structure too. Okay.
Yes, sir.
Okay. Any other question? All right. There are several important characteristics of martensite. First is the transformation from is actually diffusionless. That means carbon atom cannot diffuse out of the structure, and there is no chemical composition change. That means in the case of slow cooling, we have seen that there are two-phase regions where from austenite it starts to produce alpha iron, that means ferrite, and then there is a two-phase region of ferrite and austenite, and then there is a chemical reaction of what is that eutectoid reaction that takes place, and then you get paralitic structure when you do the slow cooling. But when you do the faster cooling to produce hardened structure like martensite, then there is no chemical composition changes actually. And it just from directly austenite to martensite is formed. And the transformation proceeds only during cooling and ceases if the cooling is interrupted. That means whenever you do the faster cooling, transformation continues, but if you stop cooling, if you keep it at a certain temperature suddenly, and then the transformation is interrupted, and then in that case, then again those paralitic structure, that means the mixture of ferrite and cementite will be obtained. Therefore, if you want to obtain 100% martensite, that means if you want to do the proper hardening, then you have to you should not interrupt the cooling process. Okay. And martensite is not a condition of real equilibrium. That means the structure is not under equilibrium, even though it persists indefinitely for a very long time. But eventually, if you raise the temperature at a certain temperature above the room temperature, then this unstable condition actually transforms the martensitic structure into ferrite, cementite, the mixture of ferrite and cementite, those structures. So this is not a condition of real equilibrium. Actually, this is the intermediate structure, and that structure can transform into different ferrite martensite or ferrite perlite, iron carbide. Those can be obtained at certain temperatures. And the most significant property is the very high hardness, and hardness of martensite increases with the increase in carbon content. Okay. And this similar property can also be obtained not only for iron and carbon, that means binary alloy system of iron and carbon, but also you can obtain this for iron nickel combination, copper zinc combination, and copper aluminum combination. You can also obtain this martensitic structure to obtain very high hardness material. The basic purpose of hardening is to obtain the fully martensitic structure, and the cooling rate at which soft product formation is avoided is called critical cooling rate. That means any cooling rate will not give you martensitic structure. For example, you heat up the steel above the upper critical temperature and then keep it at room temperature, it will not you will not be able to obtain 100% martensite. But if you cool it in the brine or in the ice, then you will obtain the fully hardened structure. So cooling rate is very critical in the formation of martensitic structure or hardened steel. In that case, the soft product means that when you cool at room temperature, that is normalizing. In the case of normalizing, you will see that there will be some transformation to produce ferrite. Ferrite is a very soft product. Okay, and if you want to obtain the if you want to complete the hardening, that means full hardening, 100% hardening, then in that case you have to cool it very rapidly, or that means you have to cool it faster than room temperature cooling. Okay, that is why it says like the cooling rate at which the soft product formation is avoided is called critical cooling rate. And critical cooling rate also depends on the chemical composition, like how much carbon is present in the matrix, or how in the case of copper zinc combination, how much zinc is present, or in the copper aluminum combination, how much aluminum is present in the matrix. These are the determining factor for what should be the cooling rate, and this can be the cooling rate that can be determined by experiment. That means you have to conduct the experiment and form the martensitic structure and check under the microscope whether the 100% martensite has been produced or not. And also it also depends on the austenitic grain size. That means the austenitic grain size that has been formed during heating. Okay, that grain size also important. If you heat it at higher temperature, then you will get smaller austenitic grain size, and then in that case you might have to use a different cooling rate than the larger austenitic grain structure. So therefore, the austenitic grain size is a very important factor for steel to form for martensitic structure. That means what should the cooling rate can be determined using the austenitic grain size. Okay, that's all about the hardening method, hardening process. Please shoot if you have any question. Okay, so the next heat treatment method is the tempering. Tempering is a very important heat treatment process because in the case of most of the heat treated part, you need to do the tempering actually. Okay, martensitic steel, as I said, the martensite is very brittle structure, very hard but very brittle. And the formation of martensite also leaves a high residual stress. There are a huge amount of residual stress also developed in the structure. Therefore, hardening is always followed by tempering. After hardening, you need to do the tempering to relieve some residual stresses as well as to obtain some toughness. That means some ductility can be enhanced. Okay, and the tempering is the process of heating the steel at some temperature below the lower critical temperature. Below the lower critical temperature, you need to heat up and keep it for some time. And time is also important factor in the case of tempering. Longer you keep at a temperature, you will get softer product. Okay, so time is also important. I'll show you a diagram showing how time is important in the case of tempering. Time and temperature both are important. Okay. And the purpose of tempering is, as I said, like to relieve the residual stresses and to improve ductility and toughness.
Residual stress.
Residual stress. Okay, the residual stress is kind of fatigue. That means fatigue. That means the internal stress. Sometimes when you wake up in the morning, you feel in your neck like your muscle is kind of stressed and you're feeling pain. You cannot rotate your head. Okay. This is called the residual stress in your muscle. That means for some reason your muscle has been a certain load has been induced in your muscle, and that is why you're feeling the pain, and that is and it is not relieving. Stress is still there. Okay, that is why you feel the pain. And similar way, this residual stress actually work because of the carbon atom that could not come out from the matrix, or that could not come out from the FCC structure, and it has formed a distorted structure. And that is why I have also mentioned that the iron matrix is plastically deformed. And because of that atomic interaction, that means one atom is exerting force to the another atom. Okay, that means carbon atom is trying to come out of the structure, but iron atom is keeping them together. Okay, and that is why because of this interaction of these two atoms, there is internal each atom is loaded at some extent. Okay, and that is why that is called the internal stress, or that stress that has been formed because of that interaction between the atoms is called the residual stress. Did you get it?
Yes, sir.
Okay. And the purpose already said, the increase in ductility is usually attained at the sacrifice of hardness or strength. But whenever you obtain a hardened structure and then you are doing the tempering to relieve the residual stress, or to obtain the ductility, or to increase the toughness, then the hardness will be reduced. Okay, that means if you want to enhance the ductility, the hardness will be reduced. If you want to increase the toughness, hardness will be reduced. Okay, that means at the sacrifice of hardness and strength, you can improve the ductility. And hardness decreases and toughness increases as the tempering temperature is increased. That means higher the tempering temperature, the hardness actually decreases and toughness increases. And we'll see that that in a different diagram, or different at various temperature. We'll see how tempering works. So this is the diagram that shows how hardness is lost with the temperature. Okay, that means when you increase the temperature, tempering temperature, then let's say the toughness actually increases at certain point and then it starts to decrease, and then again it starts to increase, but hardness continuously decreases. That means if you want to obtain a high toughness steel, then you have to have the hardness will be reduced significantly, and then you have to temper it at a very high temperature. But if you want to compromise between hardness and toughness, then this is the best option. Okay, like at 400 or less than 400, from 200 to 400 degree Fahrenheit, this is the best temperature for tempering. Then you'll get both toughness and both high hardness. Okay, so this is the diagram where you can get the information like what should be the tempering temperature to obtain what hardness or what toughness. Okay. Okay, any question? All right. So tempering, if the principal desired property is hardness and wear resistance, the part is tempered below 400 degree Fahrenheit. As I say, like if you want to have the high hardness, then you should do the tempering below 400 degree Fahrenheit. Okay, then you will get a very high hardness. And if the principal desired property is toughness, the part is tempered above 800 degree Fahrenheit, right? Because if you look at this curve, then above 800 degree Celsius, 800 degree Fahrenheit temperature, the toughness increases rapidly. Then hardness will be decreased. But in between the 400 and 800 degree Fahrenheit, the toughness does not increase much. It is almost constant. Okay, sometimes it is reduced a little bit. Okay, so this will not give you the increase of toughness. Either if you want to have high toughness, then you have to temper it above 800 degree Fahrenheit temperature. And the residual stresses that has been produced during the formation of martensitic structure can be mostly relieved at 400 degree Fahrenheit temperature. That means that within 400 degree Fahrenheit temperature, if you do the tempering, then the residual stresses are almost relieved. Then the structure will become free of internal stresses. And by 900°F, residual stresses are almost gone. That means all of the residual stresses will be relieved. And then there is another property which is called temper brittleness. Is a phenomenon when steel loses notch bar toughness and tempered at 1000 to 1250°F, followed by slow cooling. If you do the slow cooling, it still actually loses the toughness. That means there is a sudden decrease in the toughness, and it become brittle. That is a what can I say? It's a deviation from actual property. Okay, that means it is an exception. That means if you do the tempering between 1000 to 1250°F, the temper brittleness occurs, and in that case, material become very brittle, and it can be broken very easily. Okay, or if you do the slow cooling at this temperature, you temper it and cool it very slowly. There is a exceptional property of the steel. However, toughness is retained if the part is quenched in water. Okay, if you do the slow cooling, then temper brittleness occurs. But when you cool it rapidly, then the temper brittleness is not there anymore, and then toughness will be retained. Okay. Okay. Any question?
Sir, what is the notched bar toughness?
Notch bar. Do you remember when, in our first or second or third lecture we have studied iodide impact?
Yes, sir.
That is the notch bar. During the test of iodide impact, you can find out the notch bar toughness. And actually, toughness is the energy absorption. Okay,
Yes, sir.
you need to calculate the amount of energy required to break a specimen. Okay, that is the toughness. And if the bar is notched like the iodide impact test, then that is called the notch bar toughness. Okay.
Yes, sir.
All right. Okay, now let's see what happens at different tempering. Like if you use 100 to 400°F temperature for tempering. Let me first clear again what is the tempering. Tempering is raising the temperature of the hardened steel at some temperature and keep it for some time and then cool it. Okay, that is the tempering. And if you do that tempering at 100 to 400°F, structure etches dark. That means when you do the etching to investigate the microstructure, it becomes black, and that is called the black martensite. Okay, and black martensite is formed. And original as quenched martensite structure begins to lose its tetragonal crystal structure. That means the tetragonal structure that has been formed for to produce the martensite, it starts to lose. Okay, that means residual stresses are getting relieved also. And the hexagonal closed packed transition carbide and low carbon martensite are formed. That means some of the carbons coming out of the structure, and that is low carbon martensite is formed. Okay, and tetragonal structure still retains. And the CA ratio, it is the ratio of unit cell structure. For example, if I show you here, this is if you consider this is the unit cell, this is side A and this is side B, and side C is is that, and side C is usually longer in the case of martensite. Okay, and when you hit the temperature is 400°F, then this C over, if this is C, this is A, this is B. Okay, then C by A ratio actually decreases like this. This is the curve that follows. Actually indicates how much residual stress has been relieved. That means when this curve, this ratio is 1, that means there is no residual stress present. Okay. And the precipitation of the transition carbide may cause a slight increase in hardness because of the some carbon coming out of the structure and forming iron carbide, that is called the transition carbide. And because of that carbide formation, hardness slightly increases, and resulting steel has high strength, high hardness, but low ductility and low toughness. Okay, and residual stresses are relieved. And now the temperature, tempering temperature is 450 to 750 degree Fahrenheit. In this case, epsilon carbide that is forming changes to orthorhombic cementite. That means orthorhombic structure is formed in this case, and the cementite actually forms the orthorhombic structure, and the low carbon martensite becomes FCC ferrite. The low carbon martensite that has been formed for during hardening, that actually converts into body centered cubic structure ferrite. That means alpha iron is formed, and the carbide, iron carbide that is present in the structure, that becomes orthorhombic cementite. And this the microstructure, the structure that is formed is not no more martensite. The structure will be called bainite. That is called lower bainite. It's a kind of plate like structure. This is different than those needle like structure. Okay, and this is the structure that has been formed because of the tempering at 450 to 700 degree Fahrenheit. And the carbides are too small to be resolved by the optical microscope. There is very small amount of carbides are present, and it is very difficult to investigate in the microstructure. Mostly the transformed lower bainite is seen in here, and entire structure etches rapidly to a black mass formerly known as trustite. When you etch it, the entire mass actually looks very black, and the structure that is called the trustite. The tensile strength is very high, 200,000 psi, and ductility increased slightly, but toughness is still low. The hardness decreased to between 40 and Rockwell C scale. It is 40 and 60 depending on temperature of tempering. Okay. From 450 to 750, hardness becomes less than 60 actually, and greater than 40. Okay, any questions so far? Okay, if the temperature is increased, that means 750 to 1200 degree Fahrenheit, continues the growth of cemented particle, more cemented particles are generated, ferrite, more of the ferrite matrix is seen, more of the ferrite matrix is produced, and in this structure called sorbate, the carbide is resolved at 500x. That means magnification. If the magnification is 500x, you will be able to see the carbide structure, that means cemented particles. And the tensile strength is 125 to 200,000 psi, and elongation 10 to 20%. That means there is certain amount of toughness is induced. That means more energy absorption capacity has been seen. The Rockwell hardness is decreased, like 20 to 40 Rockwell C scale. And most significant is the rapid increase in toughness. Toughness increases very rapidly because of the ferrite matrix that has been produced. That means more and more ferrite matrix is seen, more and more toughness is increasing, and hardness is decreasing. And if the tempering is done at very high temperature, like 1200 to 1333 degree Fahrenheit, produces large globular cementite particle. Do you remember this structure? Can anyone say what is this structure?
Sir, spheroid?
Spheroidizing, right?
Yes, sir.
Spheroidized annealing, you can obtain this structure, but also using tempering you can obtain this structure. In this case, the cemented particles become spherical, and the structure is very soft and tough. That means huge amount of energy absorption is possible in this case, and similar to spheroidized cementite structure. That means spheroidized annealing also shows the similar structure. Okay. Okay, now the summary, tempering summary. In this case, you'll see some important things like austenite. If you austenite, if you keep the austenite at 1200 and between 1200 to 1300 degree Fahrenheit, and then the spheroidized cementite is obtained. That means round cementite particles are obtained, and Rockwell hardness is very small. Okay. And let's actually start from the slow cooling rate. Okay, if the cooling rate is very slow, that means from first assume that austenite has been produced. Okay, by heating, austenite has been produced, and at a very slow cooling rate, 0 to 1 degree Fahrenheit per second, you will get coarse perlite. That means you will get perlitic structure with the ferrite in the ferrite matrix, and the hardness is very small, like 15. Okay, if you increase the cooling rate, okay, that this is let's say the annealing, and increase the cooling rate 20 degree Fahrenheit per second, then this is normalizing, and medium perlite is produced. In this case, perlite particles are very large. In this case, perlite particles is kind of smaller particles are produced, and hardness is increased in the case of normalizing, at room temperature normalizing. And if you increase the cooling rate like 60 degree Fahrenheit per second, then fine perlite is produced. Okay, and this is like more, kind of more rapid cooling. For example, the water cooling can be can give you like fine perlite particles within the ferrite matrix. And if you increase the cooling rate, that means very high cooling rate, greater than almost 250 degree Fahrenheit per second, then you will get bainitic structure, and you have to hold it, quench it rapidly and hold it at a temperature 900 to 400 degree Fahrenheit, then you will obtain bainite, which has higher hardness 40 to 60, and greater than 250 degree Fahrenheit per second. If you cool it in the brine, that means very cold temperature, brine or ice, then you will obtain the martensite, which have greater hardness like 64 Rockwell hardness scale. Now let's come to the tempering. When you when martensite is produced and then tempering at 400 degree Fahrenheit temperature, then black martensite is formed, and certain amount of epsilon carbide also seen, and low carbon martensite is seen, and the hardness is 60 to 640. And if you increase the tempering temperature like 400 to 750 degree Fahrenheit, hardness is decreased, but more cemented particle is will be seen in the matrix of ferrite is also produced. Okay, and the changes to lower bainite. The martensite actually changes, austenite actually changes to lower bainite, and then you will get this kind of bainitic structure, and that is called the trustite. Okay, and if you increase the tempering temperature of 750 to 1200 degree Fahrenheit, then you will get sorbite. Okay, it's a small round resolved cemented particles. You will see the cemented particles and in the matrix of ferrite, and then the Rockwell hardness is also decreased, but toughness will be increased, and this will show very high toughness and very low hardness. Okay, at temperature above 1200 to 1300 degree Fahrenheit. Okay, for the tempering, there can be two different methods. Okay, first method is like you produce the martensite 100%, then you heat it up at 400 degree Fahrenheit or 750 degree Fahrenheit or 1200 degree Fahrenheit. And second method is that you cool it rapidly and keep at certain temperature, like keep at 400 degree Fahrenheit temperature. Cool it rapidly at 250 degree Fahrenheit per second and keep it 750 degrees Fahrenheit temperature. It will produce the similar effect. Okay, the both method can be used. You use the rapid cooling and keep it at certain temperature, and you do the rapid cooling to form the 100% martensite, and then increase the temperature of the martensite at certain temperature and keep it there for some time. Okay, that's how tempering can be done in both ways. Okay, any question? This is what I wanted to show you, the effect of time on tempering. The time also plays an important role in the case of tempering. Okay. If you do the tempering at, let's say, you want to obtain a hardness of 60, Rockwell CS scales, you want to obtain a hardness of 60, then you can obtain at various different way. For example, you heat it up at 400 degree Fahrenheit and keep it there for 5 hours. Then you will obtain a hardness of 60. And again, you can obtain the hardness of 60 if you heat the steel up at 600 degree Fahrenheit and within a very small time. That means within, let's say 30 minutes. Within 30 minutes, you can obtain the same hardness. And if you heat it at higher temperature, like 800 degree Fahrenheit, time is also reduced. Like within 5 seconds, you can obtain the hardness of 60. Okay, and within 2 seconds, you can obtain the hardness of 60. That means you can obtain the same hardness by tempering at various temperatures, but for you have to keep it for longer time. If you keep it longer time at 400 degree Fahrenheit, then you will obtain a hardness of 60. Okay, that's how it works. Okay, if the temperature is low, you have to keep it longer. If the temperature is high, then you have to keep it for within a small time. You'll obtain the local hardness numbers. Okay, any question?
স্যার একটু আবার বলবেন, বুঝিনি।
So let's say these curves actually shows that you have obtained a martensitic structure here, and then you want to decrease the hardness to 60. Okay, you want to decrease the hardness from 67 to 60. Then how can you do that? Okay, you can heat the steel at 400 degree Fahrenheit and keep it at 400 degree Fahrenheit for 5 hours. Then the hardness will be decreased to 60. Okay.
Yes, sir.
And again, you can heat the same steel at 1000 degree Fahrenheit. Within 2 seconds, the hardness will be decreased to 60. Okay. And decrease in hardness is related to the increase in toughness. Okay. That means toughness will be increased. Did you get
Yes.
the point?
Yes, sir.
Okay. So are you the only one attending the class?
স্যার এত
Samira?
ফাস্ট কুলিং আর স্যার
হ্যাঁ,
স্যার এত ফাস্ট
Okay.
কুলিং আর স্লো কুলিং এ দুটাই কি মানে ম্যাটেরিয়ালটা কি সেম থাকবে, টেম্পারেচার একটু আলাদা করে দিলেই?
are you talking about this graph or the previous slide?
স্যার এটার কথাই বলছি স্যার, মানে টেম্পারেচার বাড়াই দিলে এত ফাস্ট কুলিং এও হচ্ছে মানে এত ফাস্ট কি
No.
ম্যাটেরিয়ালটা সেমই থাকবে?
No, it's not like that. The material you will have a certain steel, let's say 2% carbon steel. Okay, 2% carbon steel. You have done the hardening. You got a steel that is the martensitic structure. Okay, now you heat this up at 400 degree Fahrenheit temperature, and then keep in that temperature at 400 degree Fahrenheit temperature for 5 hours. Then the hardness of this steel will become 60. Did you get my point?
ইয়েস স্যার।
Okay. And now again, if you want to make it faster, like quickly you want to get the hardness to 60, then you have to heat it up at 1000 degree Fahrenheit. Then within 2 seconds, the hardness of this structure will become 60.
ইয়েস স্যার।
Did you get it? Or did you have a different question?
না স্যার বুঝতে পারছি।
স্যার এই যে সেই ক্ষেত্রে একটা আমি 400 এও আমি 60 মিটার মানে হার্ডনেসটা পাইতেছি, আর স্যার মানে 400 এও পাইতেছি, সেই ক্ষেত্রে কি দুইটা ম্যাটেরিয়ালের আদার প্রপার্টিজ গুলো সেম থাকবে নাকি আদার প্রপার্টিজ গুলো অন্যরকম হবে স্যার?
No, other properties will remain the same. Okay, all other properties actually depends on the microstructures, right?
স্যার
The chemical composition is same. The only thing that is changing is the internal structure. That means the crystal structure. And if you heat it at larger temperature, the change occurs rapidly. If you heat it at lower temperature, change occurs slowly. But it ultimately goes to the same structure, right?
Yes, sir.
All right, any other question? All right, so there is another thing that is called surface heat treatment. So far we have studied like bulk heat treatment processes, but now we need to know the surface heat treatment. That means there are some surfaces that needs to be treated because those surfaces are often needs to make them scratch free or sometimes small impact resistant. Okay, And in that case, you need to do the surface heat treatment or case hardening. It's the same. Surface heat treatment or case hardening is the same process. Case hardening means a certain layer of the material is hardened, not the whole material. The internal material will remain the same, but the only surface will be hardened. Like for example, if you want to talk about the lathe bed, the surface has to be really hard, but internal structure, it doesn't matter whether it is hard or not. Okay, so in those purposes, surface heat treatment is necessary. The many industrial applications need a hard wire resistant surface called the case and a relatively soft, tough inside called the core. Sometimes you need to have the surfaces hard, but the core is soft or tough. Okay, so in that case, you need to do the surface hardening. There are 5 principal methods of case hardening: carburizing, nitriding, cyaniding, flame hardening, and induction hardening. There are 5 different methods that can be used for surface heat treatment. And first 3 methods in here, like this 3 method, actually change the chemical composition. That means chemical composition of the metal surface is changed to get the hardening, to obtain the hardened property. Okay, to increase the hardness. And the carburizing by addition of carbon. That means in the case of carburizing, you add the carbon to the surface of a metal. If this is the surface, in the surface you add more carbon, so it becomes hard. Okay. In the case of nitriding, addition of nitrogen, nitrogen is added to the surface of the material to form a certain layer of hardened steel or hardened material. Cyaniding by addition of both carbon and nitrogen. That means chemical composition of the surface is changed or modified to obtain a hard surface. Okay, either by nitrogen, oxygen, carbon, or carbon and nitrogen both. Okay. And the last 2 methods do not change the chemical composition. Without changing the chemical composition, last 2 methods, the hardening can be obtained on the surface of the material. Okay, so actually I want to stop for today here, and in the next class we will be discussing all the surface hardening methods, and also hopefully the TTT diagram will also be discussed in the next lecture. And because I have the meeting within a short time, so I need to go.